Okay, so we're starting our stoichiometry unit, and a bit of an intro that you need to have are these two terms here up on the board, quantitative and qualitative analysis. And so both of these words are really important in science. You need to know the difference between the two of them, and so that's why we start this unit off with kind of this introduction. Qualitative analysis really has to do with or deals with descriptions. So descriptions of maybe characteristics or things that you can see, taste, smell of chemicals. And obviously certain chemicals you wouldn't smell, certain chemicals you wouldn't taste, but there are some descriptions that we can give all these chemicals, and that's what we refer to as qualitative analysis. It really deals with the qualities that that chemical has. Quantitative analysis deals with numbers. So we're talking about calculations and just numbers in general. And quantities is where that word comes from. So distinguishing between the two is really important. You can see if you look back to the acid-base unit, we talked a little bit about qualitative analysis for acids and bases. Litmus turns red or blue. It's got a particular taste, maybe sour or bitter. And then we dealt with some quantitative analysis, so pH scales, calculations of hydronium and hydroxide ion concentrations. And so these are just some things that we've dealt with. You're going to see it again as we move into this unit, and connecting it to these two terms are important. So our first main concept in the stoichiometry unit is this concept of net ionic equations. And we've kind of arrived now to the point where, if you remember, I've been kind of talking to you about this all semester that you really need to get good and have a good habit formed of writing in your states of matter. And we're now at this point of the semester where this becomes super important. And you have to write in the states of matter in order to be able to do these problems correctly. So what a net ionic equation is it actually kind of describes exactly what's going on with a particular chemical reaction. So as we've kind of talked to you about at the beginning of the semester and in Science 10, chemical reactions, and we talked about double replacement, single replacement reactions. These are really good approximations of what's happening, but to kind of get into a little bit more of the details of what's really going on now that you have a base knowledge of what is a dissociation and an ionization of ionic and acids, ionic compounds and acids, you can kind of now use this information to understand a little bit more fully what's exactly happening with chemical reactions. So here's a typical double replacement reaction that I've written up here on the board, and you can write these from word problems as they give you a description. This actually turns out to be question number 1 in your practice booklet. So if you want to follow along with me there, and you can kind of read that problem and see how it corresponds to this, you can see that I've done two things. I've written the double replacement reaction that's balanced, so you can see that I've balanced this reaction, as well as you can see that I've included the states of matter. Now oftentimes I get the question, where did these states of matter come from? And if you remember in your data booklet, because all of these are ionic compounds, then I've used the solubility chart in your data booklet to identify whether these substances are soluble in water or not. If you recall back, I oftentimes talked about how chemical reactions have to take place in water in order for them to really take place in any short period of time. And the reason for that is because when we dissolve things in water, it spreads the chemicals out, and they can all kind of interact simultaneously, which speeds things up a lot faster. So we drop all of these into water. These two reactants are soluble in water. If you confirm that in your solubility chart, you can do that and see that. And then we've got these compounds over here, and I've identified whether they are aqueous or not. And you can see that this compound, lead 2 iodide, turns out to not be soluble in water. So we call that a precipitate. And this actually is like a really bright yellow precipitate that when we mix these two substances together, we get that substance on the product side. So here's the rules that I've written down on how to write net ionic equations. And really, it just is a function of you just following these rules from top to bottom and making sure that you're doing exactly what they say. If you do exactly what they say, then writing these net ionic equations are really, really simple. The first rule is, as you have already noticed, I've stated, is just to write a balanced chemical reaction including all the states of matter of those substances in there. These are all ionic compounds, so I just use the solubility chart to identify that. If it's an element, then you just look on the periodic table, all the states of matter of all the elements are in there, and so that becomes quite easy as well. And I've given you some rules over the course of the semester as to how to write states of matter in for certain substances. The second rule is what you have to do is you have to dissociate all ionic aqueous substances. And the rule here is that they have to be ionic and aqueous in order to split them up into their ions. And so you can see this is an ionic compound and it's aqueous. And so what I've done here is I've just written out what actually is in the beaker. So instead of lead 2 nitrate being in the beaker as a compound, we know that that isn't the case. When I stick something that's soluble in water, then it's going to dissociate into its ions. And in this case, this is made of lead 2 ions and nitrate ions. Now, because I've got 2 nitrates here, you can see that I've written 2 nitrates down below, just like I would on a normal dissociation equation. So I've just written them here, and then I carry on. So right here, you can see sodium iodide is also aqueous and ionic, so I've dissociated that as well. And you can see that those substances there come from sodium iodide. Now, because I've got a 2 in front, that means that I'm dissociating 2 of these molecules, or 2 moles of these molecules. And so I need to say here as well that I've got 2 sodium ions and 2 iodide ions. That's something important to note. Again, this one here is an ionic compound, and it's aqueous, and so I've dissociated that as well. You can see, again, 2 sodium nitrates, so I've got 2 sodium ions and 2 nitrate ions right there. And then this one here is an ionic compound, but it is not aqueous, so I do not dissociate that substance. I just write it as it was listed before, so PbI2. And this makes sense because when this is in the beaker, this just falls to the bottom of the beaker as a precipitate. It's just a solid, and so it remains as its compound lead 2 iodide. The next step here says that if you have any strong acids, you need to ionize those, and we ionize them into hydronium and the anion of that strong acid. Now, in this example, there are no strong acids, but in the next example that I'll do in the next clip, I'll illustrate that. The fourth example, or the fourth rule here, is to identify and cancel all spectator ions. So by definition, what is a spectator ion? A spectator ion is just an ion that is occurring or exists on the reactant side of the equation and the product side of the equation. Essentially, what it means is that if you have a substance over here and over here that is exactly identical to itself on both sides of the equation, it's not involved in the reaction. It didn't go through a change. And so because it didn't go through a change, it's not involved in the reaction, therefore it's watching the reaction happen. These ions exist in the beaker, they're there, but they're not part of what the net reaction really is. And so you can see I've got a few substances that are like that. I've got the nitrate ions, 2 of them on this side and 2 of them on this side. And I just want to cancel them out. They're not doing anything, so they're not part of what's really going on. They're just there. I also have 2 sodium ions on either side of the reaction. And so those are spectator ions as well, so I cancel those out. And what you can notice is the ones that I have left over right here, lead 2 ions, iodide ions, and my lead 2 iodide, these guys don't cancel because these guys were separate before and now they're bonded together after. And so my net ionic equation is going to be just rewriting all the remaining substances that are left over. And so I've got Pb2 positive plus 2I minus aqueous for both makes lead 2 iodide. And that's my net ionic equation from this starting point. So in the next clip, I'll go through another example with you that involves an acid, Be right back, hang with me. So here's two more examples that I want to go through with you guys to just illustrate some of these rules and some of the things that you need to be aware of as you kind of come across some other reactions that are not double replacement reactions in trying to write net ionic equations. So this first one is this acid example that I told you I'd go through. I made one adjustment to the rules, and it's just for the purposes of balancing these reactions. So we know that acids, when they're put into water, they make hydronium, H3O positive. But to simplify things and to make things a little bit more easy and for the purposes, as I said, for balancing the reaction, what we're going to do is when we ionize any strong acids, we're going to ionize it into H plus and its anion. So I've made that adjustment there in the rule. Please make that adjustment in your notes as well. And so here's this just really simple sentence that describes the chemical reaction. We have nitric acid reacting with sodium hydroxide. So you can see my nitric acid reacting with sodium hydroxide here. And then I've written my double replacement reaction. Now, because this is a strong acid, I'm going to ionize it into H plus and NO3 minus, aqueous. My sodium hydroxide has been dissociated because it's an aqueous ionic compound. And my sodium nitrate has also been dissociated as well into sodium ions and nitrate ions. You can see water, HOH, is a liquid, so I don't dissociate that. It's not ionic and it's not aqueous, so I just leave it alone. Then I identify my spectator ions, I cancel them out, as you can see I've done there, and then I write out what's left over. My H plus my OH minus gives me my HOH, liquid or water. And so this is just a net ionic equation that really shows what essentially is a neutralization reaction, where we have an acid reacting with a base, an acid reacting with a base, and it makes a neutral substance, which is water. So that's that example. This example over here is where we have iron reacting with copper 2 sulfate, and you can see my reaction written up above. This is a single replacement reaction. And so you can see that I've written the elements as solids because that's what they are. They're metals. At room temperature, they're going to be solid. And so I've got iron solid reacting with copper 2 sulfate solution, and that's going to give me copper solid and iron 2 sulfate solution. And so over here in the second row, I've dissociated all ionic aqueous compounds. So the only one that I've done over here is copper 2 sulfate into copper ions and sulfate ions. The one I did over here, iron 2 sulfate into iron ions and sulfate ions. You can see that iron solid and copper solid have been left alone because they're not ionic and they're not aqueous, so I just leave them as is. Now when I cancel my spectator ions, you can see I've only canceled out the sulfate ions. And the reason why is because if you take a look, iron solid turned into iron ions. That was a change. Yes, it's the same atom in terms of they're both iron, but this one is a neutral substance, and this is a charged substance. So it did undergo a change. And so I don't cross off iron solid with iron ions. They're not the same, so they're not spectator ions. Same thing with copper here. You can see it changed from copper ions to copper solid. And so the change is simply that. You can see that there's a transfer of electrons there between those two substances. And so I've written that down here below. Iron solid plus copper ions makes copper solid and iron ions. And that's my net ionic equation for that. So really, guys, like I said, it's just a function of following the rules pretty closely, and you should be just fine as you're doing these. And so good luck as you're starting to tackle this concept. Have a good one. See you in the next video.